The link is not allowing me to mute the YouTube. Good evening. Welcome to the discussion for week 11. Mahesh, is my audio clear? Okay, fine. Okay, fantastic. So, as usual, please type in your questions if you have those, and I'll be addressing them. But we'll follow a regular agenda. We will first discuss what were the topics that are being discussed. This week we saw, in fact, two sections. One was on basically details of coherent detection. So all these topics that I have marked here from here to here, these were related to coherent detection. Now, as I said during the lectures, this idea of balance detection came in even before we started modulating the phase, because balance detection is a good way of reducing the common mode noise. So earlier, to improve the link budget, people had started using coherent detection, essentially with a heterodyne detector with a local oscillator, to push the detection into the short noise dominated regime. But when we started modulating information in phase, this became more of a requirement. And so we saw the evolution of the different detection processes. First, we saw the case of a simple balance detection. Then we saw how we can use this balance detection when you have polarization diversity, because a balance detection would always have a local oscillator. And then you will always ask this question, what do I do with a local oscillator, in the sense that how do I match the polarization states of the input wave with that of the local oscillator. And then we say, okay, I can always use a polarization diversity scheme. So you used a polarization beam splitter and used a diversity scheme to make sure that both the polarizations of the input signal are received by the coherent receiver. Your data need not be modulated in both the polarizations, but still you would want to extract the information from both the polarizations, simply to make sure that you are not losing any power, signal power, or you're not losing any information carried. You're not basically having a trade-off in signal power. Then we talked about how it's important to have phase and polarization diversity, because even when you do a polarization diversity, you realize that there's always a phase locking required to make sure that the local oscillator phase and the incoming phase, I mean the local oscillator phase, there's no time dynamic fluctuations in the local oscillator phase. And in electronic systems, that is taken care with different phase lock loops. You would have heard of Costas loops and things like that. But in optical system, we don't do that. Instead, we use a 90-degree hybrid. So this the phase diversity was possible with the 90-degree hybrid, and the polarization diversity is possible with the polarization beam splitter. So we ultimately ended up with some nice phase and polarization diverse coherent receiver, and that was rather that structure is what we use in today's coherent communication systems, right? So I have given you the block diagram of how a phase and polarization diverse coherent receiver will ultimately work for us, which doesn't require any phase lock loop. So at the output, you will have 4 balanced photodetectors, and you will start digitizing those outputs. And from the digital data, we can calculate what is the polarization, what is the phase of the phase and amplitude of the input signal. That brings us to the next topic, which is the impairments. When I say impairments, it means the irregularities or what are the distortions that the signal goes through. And we have seen that these distortions can be classified of those happening at the transmitter and the receiver. So this has to do with the laser, the phase noise of the laser, and the frequency offset between the transmitter and the receiver lasers. And I have given you a brief description of how to generate them in MATLAB and how to construct the digital signal processing compensation. This would be familiar to those who have done any DSP course before, but for those who have not done any DSP course, it may require a little bit more time to understand. But we are not questioning, or we are not asking you any assignment questions or any end semester questions based on the digital signal processing. This is for more of, so this content is more of for information rather than evaluation, right? So if people are more interested in this, you can take it up, because I've given you some very basic codes on how to actually work out these signal processing algorithms in the most simplified, straightforward manner. And you could use that, try it out yourself. But as I said earlier, this is more of towards information rather than towards examining you on this. So that was the content. If you have any questions, please go ahead and share right now. Otherwise, I will start moving on to the assignment questions. So, as I told you earlier, the assignment questions are based only on the first part of this, which is on balance detection. I have not put in any assignment questions on the part which requires signal processing, and that is intentional. That is to just keep it simpler for you. And going ahead with the assignment questions. In fact, the number of questions are also limited. So, in fact, if you have carefully followed the class, these questions are actually very trivial. Let's say you have an ideal 90-degree hybrid. So the block diagram of the ideal 90-degree hybrid is given to you. And you have the local oscillator with an electric field ELO. This is the local oscillator. And let's say the output of the 2 ports of the 90-degree hybrid is represented as E1T and E2 of T. And each of them is allowed to fall on a photodetector, which is PD1 and PD2. And these outputs are referred to as I1T and I2T. This is the premise of the question. So the question says that we have seen that 90-degree hybrid can be used in a coherent receiver to obtain phase diversity, and you can avoid phase lock loop here because you are measuring the phase at every instant of time. So one such arrangement is here, and the input field, we are assuming that it is given that E1 of T is signal. This is the amplitude part of the signal. E power j omega s is the frequency of the signal, plus phi s is the phase of the signal. This phi s of t could have the phase modulation that you're trying to extract. And given that ELOT, the local oscillator field, you're representing as ALOT, Ideally, this amplitude should not be a function of time, but then I'm saying that there could be some amplitude fluctuations. E power j omega LO, this is the center frequency, which should be as close to signal frequency as possible, plus a phi LOT, which is the phase of the local oscillator. And I'm defining omega IF is equal to omega S minus omega LO. And I'm defining delta phi S as the phase difference, instantaneous phase difference between the signal phase and the local oscillator phase. And the transfer function of the hybrid is given to be 1 by root 2, 1 e power j pi by 4, e power j pi by 4, and 1. Responsivity of the detector is RD. Okay. The first question is to find out the photocurrent. So it's very simple. It's a question of doing the right algebra. So since the transfer function is given, this transfer function is actually given to you as this matrix. So you can just find out what is E1 of t and E1 of t and E2 of t. E1 of t times matrix E1 of t is 1 by root 2 transfer function times 1 e power j pi by 4, e power j pi by 4, 1. Now, input is Es of t in one arm and ELO of t in the other arm. You have to notice that this transfer function is written for field, whereas what we are asked to find is the photocurrent. So from this, you can write down what is the expression for E1 of t, and you can find out what is the expression for E2 of t, and this is just expansion of this matrix. And the photocurrent I1 of t is, the photocurrent we know is proportional to the intensity, and intensity we know is proportional to the modulus of electric field square. So I could write this as E1 of t mod square. So you will get a complex expression here. I'll write it down for first case. It is 1 by root 2 Es of t plus e power j pi by 4 ELO of t. You see the 90-degree hybrid build is already here. There is a pi by 4 phase shift here and a pi by 4 phase shift here, which means that the output, let's write out E2 of t. This is 1 by root 2 e power j pi by 4 Es of t plus ELO of t. Right? So if you now expand this, you will I mean, e power j pi by 4, you can now write it as cos pi by 4 plus j sin pi by 4. And then you can do a modulus square here. That will give you your I1. Similarly, the next question was to find I2 of t, and that is equal to RD times E2 of t mod square. Right, so it's a question of substituting it algebraically and finding out what this expression is. There's nothing more here. The next question, of course, you will have to do substitutions of Es of t as here. Here, this is Es of t, and ELO of t is from here. So you have to substitute. And that when you're doing mod square, how do I do this? You will have to do 1 by root 2 EST plus e power j pi by 4 ELOT times EST conjugate plus e power minus j pi by 4 ELOT conjugate. And this will give you the modulus square value. So this becomes 1 by 2 because there is a 1 by root 2 times 1 by root 2. And ES conjugate will be mod ES square, that is mod AS square. So you can do this expansion and find out what is the corresponding expression for the photocurrent. Now, if you look at the choices, you will realize that there is some learning there in the choice that I have given there. You'll realize that there is a DC term and there is an AC term. And unless you use a balanced photodetector, you cannot cancel out the DC term. The DC term will be present. And what we have said, PD1 and PD2 are regular detectors. They are not balanced detectors. If they happen to be balanced detectors, then if there is any common mode DC current that is generated, for instance, if my output has a DC current, and if the input is it is fed to a balanced detector instead of a regular detector, you have a chance of cancelling out the common mode DC current, and you can just retain only the AC part of it, right? So that's where you can also understand the importance of balanced detector. So you can find out photocurrent I1 and I2. And then what I'm asking you to find is the sum of I1 square, sum of squares of photocurrents. So I2 square. So you'll have to substitute this. You would get the photocurrents. You find the sum of squares. And the reason I'm asking you to find out that is that sum of squares will squares of AC components will actually give you the signal current, the signal power. So if your data, so this will give me my signal. In fact, it will give you AS square. Okay, this will be proportional to signal. You have to actually find out how much is the proportionality constant and so on. But this is going to give you AS square. And the learning from here is, if I just fed this and then if I sum these I1 square and I2 square, what I end up having is something proportional to AS square, which means I end up having something which is proportional to the signal power. So this part is what I would do when I have on-off key data, or if I have, let's say, PAM4 data, which will actually recover only the amplitude. It will recover only the power, because if you're not interested in finding out the phase, all what you need to do is to do the sum of squares of this current. Okay. But if you're interested to find the amplitude, in addition to amplitude, if you're interested to find the phase also, if you do the sum of squares, the phase information is lost. So you have to do something else. Okay. So what I'm trying to say here is that this kind of arrangement is not suitable only for determination of phase. Even in a situation where you want to actually determine the amplitude, you can still use this. Okay. So the next question is, this is question 1, this is question 2, and this was question 3. And in question 4, what you have is, you're saying that in a way, one way to realize a hybrid 90-degree hybrid is to use what is called as a 3x3 coupler. You learned about these coupler designs in the previous module, where I've said that you can use you can fabricate a directional coupler by tapering and fusing and so on. So a 3x3 coupler is made, and the transfer function of the 3x3 coupler, which is essentially a 3x3 matrix, that is given to you. And the assumption is that you are using 2 inputs and 2 outputs of this coupler. So this input you are giving ES of t, this input you are giving ELO of t, here you are taking out E1 of t, and here you are taking out E2 of t. So the third, there are 9 elements here. These elements, which are the outer elements, they will not contribute because you are neither giving an input nor taking an output from this, because you are giving an input only EST and ELOT. So, and there is no input here. So irrespective of the value of this matrix, elements of this matrix, it's not going to matter. It's only this square part that is going to matter. And if you look at the square part of that matrix, you will have some elements that are written up. I mean, I've given you the elements of that matrix. In this case also, I'm asking you to find out the AC component of I1T. So the method is the same. You will find out E1T, E2T in this case as multiplication of this 3 by 3 matrix with this input matrix. And well, I should also say this is not 2 element, I should say it's a 3 element, right? So but then of course you're not interested in the third element, you're interested in finding out what is E1 and E2 in terms of ES and ELO. So it'll come out to be a long algebraic expression. So write down that expression, find out what is E1 of t and E2 of p, and from that you can go back and use the same relation here, that I1 of t is R of E1 of t. Of course, this E1 of t is what you get from this matrix. And similarly, question 5 is to find out what is I2 of t. And question 6 is to find out what is the sum of currents. Now, interestingly, in this case, also you will find out the I1 square t plus I2 square t is also, in this case, also proportional to AS square. It's just that the proportionality constant will be different when compared to a 2 by 2 coupler. Now, that will result in different signal to noise ratio if you are using a 3 by 3 coupler versus a 2 by 2 ideal hybrid. So the last question is about finding out the signal to noise ratio, assuming that the noise power is the same. So if you can find out the ratio of the signal powers, signal power with, you can find out what is the signal power with ideal hybrid, and you can also find out what is the signal power with a 3 by 3 coupler. The ratio of these two will give you the signal to noise ratio change, because I'm saying that the noise power has not changed. In reality, the noise power will be also slightly different, but you can get an order of magnitude change. And the last question is, suppose we are using this integrated optic approach to realize the 90-degree hybrid. In that case, what is the change in signal to noise ratio? So you have to go back to the lecture. This is a task for you. I'm not going to give you the answer. Go back to the lecture, write down what is the transfer function of the 90-degree hybrid that we have used there in the lecture, and then work out this I1T and I2T and, you know, find out the change in SNR in that case. So that is question 8. And I think the assignment ends with question 8. So I'm done with my discussion of assignments. If you have any questions, you please ask now. I'll wait for your questions for another five minutes. And if not, we will log off. So please ask your questions if you have. I don't have any questions in the feedback form or in the Excel sheet or the feedback sheet, but I'll still wait for 5 minutes to see if you have any questions. I mean, these expansions of these are all similar to what we did in class, so you should be able to work out the same way. Okay, Mahesh, I don't think there are any questions now, so we will log off and request the students to ask it in the forum if you have any questions.